Hello students, so we will start with group theory today. And this is a very important aspect of mathematical physics, and it is used in a lot in spectroscopy, crystallography. So we'll take up one aspects one by one. So we'll first start with the word group, how to define a group. So a group G is actually a collection of elements with a rule to combine. So it's a collection of elements. That's the first thing. The second thing is that there's a rule to combine. Two elements, any two elements, and this process of combination is called group operation. Now, this group operation, it again has to satisfy certain properties. There are four properties which the group operation must satisfy. The first property is called closure property. That means if A and B are two elements of a group, then A suppose we obtain this property by start. So A star B is equal to another element C. This is the closure property. The second property is the associative property. It means A star, well, let's represent it by a dot. So for associative, A dot B dot C is equal to A dot B dot C, where ABC are the three elements of the group. The third property is the existence of an identity element. That means there has to be an element E such that any element, if it gets operated by this identity element, it gets back the original element. So it's called identity element. So it's the third property. And last property is there should be an existence of an inverse for each and every element. So that if A is an element, then there has to be an A inverse of that, so that on group operation with that inverse you get by the identity element. So these are the four properties: closure, associative, identity, and inverse. So let me write them once again. So the four properties which should be satisfied are closure, associative, identity, and inverse. So these four operations, these four properties are satisfied by this group operator, and so we can consider them as a group. D is a group. Now, apart from these properties, we can have certain lemmas based upon these group operations, like uh, we can say that group operation is not commutative. Usually, generally, that means A dot B is generally is not equal to B dot A. However, if this case is there, then that group is called an abelian group, where the group operation is commutative. Now, what we will do, we will define certain operations, and like we'll take an example. We'll first say that there are four numbers: 1, I, minus I, and minus 1. And these four numbers, they are forming a group G under ordinary multiplication. So here the group operation is multiplication. So we can group is usually presented in this way. So G is a group, then it should have the elements A, B, dot 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 dot. It should have an inverse, A inverse, B inverse. It should have the identity element, and it should have an operation. This is how the group is defined. Okay. So we have this four-member group, and we have to see that whether they are forming an actual group or not. So we'll take one by one. So if we multiply any two elements, so say we take up first two elements, 1 and I, if we multiply them, so it is giving back I. So if we multiply I and minus I, so it is giving back 1. Minus I, again I to minus 1, minus I. So any operation we do with any two elements gives you back another element. So the first condition is satisfied. The next condition is of associative property. So if I gets multiplied by say minus I into say 1, and so it is very much equal to I getting multiplied by minus I and then 1, and it is true for all the 4 elements. So the second property of associativity is also proved. Now we need to find out the identity element. So here identity element is of course 1. Identity element is 1. So any element multiplied by this identity element will give you back the original element. So this is identity element. And the last one is your inverse. So to find out whether each one has an inverse of its own, so we will take up the first case. Say first is 1. 1 is inverse of its own. So 1 into 1, it gives you 1. Minus 1 is also the inverse of its own. Minus 1 into minus 1 is equal to 1. I has inverse minus I, it gives you 1, and so is the case with minus I. So I and minus I are inverse of each other. So these are self-inverse elements and they are inverse elements of each other. So we say that all the 4 conditions are satisfied. So we can say that this is indeed a group. Now let's take another example. Let's assume that there are 4 matrices. The matrix E is identity matrix 1 0 0 1. Then we have a matrix A 0 minus 1 1 0. Matrix B minus 1 0 0 minus 1, and matrix C 0 1 minus 1 0, and so matrix multiplication. So the operation is matrix multiplication. So you have to find whether this 4 matrices they form a group or not. So what we can see here is we have an identity matrix E. So this is obviously is the identity element. So the first one condition is satisfied. Secondly, you have to see whether any 2 elements is giving you back the any other elements. Let's say take 1 0. Say A minus 1 1 0, if it's multiplied by say B minus 1 0 0 minus 1. This is A and this is B. So we'll get 0 minus 1 1 0 0 0 minus 1 1 0 0 1 minus 1, then minus 1 1 1 and 0. So this is actually C. So A into A dot B is equal to C. Let's take another example. Let's multiply B and C. So let's take B, that is minus 1 0 0 minus 1. This is B. If it gets multiplied by C, So we get minus 1, 0, 0, minus 1, we get 0, then we get minus 1, 1, 1 here, we get 0, 0, minus 1, and again 0. So this is A. So B dot C is equal to A, and similarly we get C dot A is equal to B as well. So we see that any two multiplication of any two matrices of the group is giving you another matrix which is also an element of the group. So the first condition is satisfied. Also the second condition, that means A dot B dot C is equal to A dot B dot C is also satisfied. Now the question is the inverse. What is the inverse of A? Inverse of A is that it's adjoint A divided by A. This is the inverse, and this is equal to 1. And what about the adjoint of A? A is simply 0, minus 1, 1 and 0. So this is nothing but C. So and this is A. So A inverse is equal to C. What about B inverse? So I take B inverse is again adjoint B by determinant B is again equal to 1. So the adjoint of B is minus 1, 0, 0, minus 1. So it's by B. So you get back to B. So B inverse is actually equal to B. This is the self inverse. Okay, so so the inverse condition is also satisfied. Hence, we can say that this is a group consisting of the following elements, where all the conditions of the group have been satisfied.